Hello, I'm Doug Montgomery, and I'd like to welcome you to our fourth Fireside Chat for our experimental design courses in Coursera. We're recording these Fireside Chats, and the previous three have already been recorded, and they're posted in, you can find them under the Resources tab of your Coursera course. And we'll post the recording for this one as soon as we're done this morning. A couple of reminders about things. The mics are muted and videos are turned off when you join. Please don't turn those on. It just would be too confusing. And if you have a question or things that you would like for either me to talk about or our guest today, Dr. Dan McCarville, you can request that or type in your question in the chat function on the Zoom menu bar. And so you don't really need to wait until the Q&A part of this Fireside Chat. You can do that really at any point. And if we don't get to all of the questions that are asked during our Fireside Chat, we'll get those questions answered and we'll respond to it in Coursera. We have a special guest today, Dr. Dan McCarville, and I'll tell you a little bit more about him when we get to his part of the program shortly. He's a really interesting guy, and I've known him a long time, and I think you will really enjoy his presentation. His presentation has to do with experiments with mixtures. Now, we talk a little bit about mixture experiments in the third course in the specialization. That's the response surface material. Because mixture experiments are just a special type of experimental design in which the factors in the experiment, they are the ingredients of a mixture, and they're usually called proportions of a mixture because they typically are measured on a proportion basis. And the response variable from the experiment is a function of only the component proportions. And so what makes these things unique is that the sum of all the component proportions for any run in the experiment has to be unity. And this is on a weight basis or a volume basis or mole ratio, whatever your unit of measurement is. But the proportion of ingredient 1, x1, plus the proportion of ingredient 2, x2, plus all the way out to the proportion of the last ingredient, x sub q, the sum of all those proportions has to add to a constant, and we'll take that constant to be 1 or 100%. People have been doing mixture experiments for a very, very long time. They're probably some of the earliest types of experiments that human beings have run. And I always tell the students in my ASU class when we talk about this that even Shakespeare knew about mixture experiments. Did you know that? Yeah, even Shakespeare talked about mixture experiments. Now, I don't think he really understood what a mixture experiment was, but here's the example, okay? The play where the Scottish knights are coming back to the castle, Macbeth, okay? After a hard night of carousing or whatever it is Scottish knights do, okay? And they encounter the three witches, okay? And I remember the movie Macbeth, which was made, I think, in the 1930s. And I remember the scene very, very well. The knights ride up to this little hillside, and there are the witches. And what are they doing? They're making a witch's brew. So how do you make a witch's brew? Well, a witch's brew is made up of eye of bat, toe of newt, wart of frog, and water. It is a 4-component mixture experiment, okay? And the sum of all those component proportions adds to 100% of the volume of the pot. So there's an example of a 4-component mixture experiment, okay? Now, Their experiment was actually more complicated than that, because if you remember the scene from Macbeth, the quote from the witch is something like, double, double, boil and trouble, fire burn and cauldron bubble. That's the line. I'm sorry I mangled that. I don't do Shakespeare very well. But what are they doing? Well, they're heating the mixture. Okay, so temperature is another factor. It's not a mixture component, it's what we call a process variable, because it can be independently adjusted. What else are they doing? They're stirring the mixture. Okay, so stirring rate or agitation rate is a second process variable. And finally, what else are they doing? They're chanting. Double, bubble, boil, and trouble, fire, right? Okay, so another process variable is chant or no chant. Okay, that's a categorical process variable. So this is a fairly complicated mixture experiment, and these kind of experiments occur all the time. Now, I mentioned that the sum of all the component proportions has to add to unity, and that causes some kind of interesting things to happen in the experiment. And I need to advance the slide. Okay, all right. And my little clicker isn't advancing the slide. Whoops. Okay. Here's what I mean by the component proportions adding to a constant. Suppose you had two factors. Let's call them x1 and x2. Okay, and there are no constraints. Then either factor x1 or x2 can be varied over the range from 0 to 1, let's say. So if there are no constraints, then you can run experiments anywhere you want in that square that you see on the left hand, the A side of this figure. But if these are mixture components, then x1 plus x2 must add to 1. And so the only place that you can run an experiment is where in that space, x1 plus x2 adds to 1. And the only place that that happens is along that diagonal line going from the upper left to the lower right. With three factors, something very similar happens. If you have three factors, x1, x2, and x3, and they can all be varied from 0 to 1, then you can run experiments at any location in the cube that you see on the right in the B figure. But if you have mixture components, then x1 plus x2 plus x3 must add to 1. And so you can only run experiments in that region where that constraint is satisfied. And that's going to be where? That's going to be at the locations where each variable is equal to 1 and the other two are equal to 0. Those are the points that you see on the corners of the cube, lower left, lower right, upper center. And then all of the places where x1 plus x2 is equal to 1, or x1 plus x3 is equal to 1, or x2 plus x3 is equal to 1, they are the diagonals going through the cube. And then the shaded area in the center is where all three of the components are non-zero, but the sum is equal to 1. So that triangular region that you see, that's the feasible design space for these mixture components. This leads to a coordinate system for mixture experiments, such as you see here. This is what's called a simplex coordinate system, because that triangular region is known as a simplex. And so the way this coordinate system works is along each of the edges, these are called flats usually, along each of the edges, two of the components are non-zero, but the third component is equal to 0. And then if you go from the center of that along the axis to the opposed vertex, you are increasing the proportion of that ingredient and decreasing the proportion of the other two ingredients relative to the increase in the first one. And the center of that region that you see, where the three coordinates cross, that's the centroid of the mixture space. And all of the ingredients are equal to a third at that location. We can have many variations of these mixture experiments. You can have constraints. say, a lower bound constraint. You have to have a certain minimum amount of each ingredient, or an upper bound constraint. You can't have more than a certain amount. Process variables and mixture components in the same experiment. That's the Shakespeare example. Order of addition experiments. This happens sometimes when there are chemical reactions occurring. You have to put in A before B. Mixture amount experiments. The response variable depends not only on the mixture in ingredients, but also on the amount of the material that may be used. That happens when the ingredients or the components of, say, a fertilizer. As I said, a mixture experiment is a special type of response surface experiment. Two differences. The design space is different, so you have constraints, and so you need special types of designs to handle that. And the form of the response surface model has to be slightly different because the constraints on the mixture space restrict the form of the model that you can fit. Mixture experiments have been around for a very long time, but they weren't really formally studied until the late 50s and the early 60s by a very, very famous experimental design statistician named Henry Chaffee. And Henry Chaffee created a class of what are called lattice designs. And you see on the slide here, simplex-lattice designs for 3 components and 4 components. The 3-component designs are the triangles at the top, and the 4-component designs are the figures that you see down at the bottom, the little pyramids. And on the left of each of these, you're looking at designs that can fit a quadratic mixture model, and on the right, you're looking at designs that can fit a cubic mixture model. I mentioned that there were special mixture polynomials, mixture models. These are the Chaffee mixture models. The linear model is just a linear combination of the ingredients, no intercept term. The quadratic model is the linear model plus what we call the binary blending terms, the cross product terms. You notice there are no squared terms here. You can't have the squared terms because of the structure of the design and the constrained region. And similarly, there are full cubic and special cubic type models as well. Most computer software packages that have mixture design capability, Jump and Minitab, for example, they fit these models and do a very nice job of that. When you have constraints on the component proportions, then what happens is that the shape of the design space changes. If you only have lower bound components, then the design space is still one of these simplexes, and you can still use a simplex type design. But when you have both upper and lower bound constraints, then you start to run into a problem. Here's an example of a mixture experiment that has only lower bounds. And you can see when you impose those lower bounds that the feasible region that you can use in the experiment is still a simplex. It's a smaller one that's embedded in the original simplex region. But when you have both lower and upper bounds, as you have here, then the simplex region becomes constrained. And now what you've got is this sort of polytope region that you see in the middle of the original simplex. And so simplex designs don't work. And so that's when we end up using optimal designs. People typically use either a d-optimal design or an i-optimal design in these types of constrained regions. There are also space-filling designs that work really, really well. There's an option in Jump called fast flexible filling. Works really, really well for these types of constrained designs. So with that, we're sort of done with my part of this, and I want to introduce our guest today, Dr. Dan McCarville. Dan is a professor of practice here at ASU, and he came here a few years ago to start up our program in engineering management, and we have a very successful engineering management undergraduate degree program and an online master's degree program in engineering management, which Dan has done a great job of putting together. I've known Dan for a lot of years. He originally after completing his undergraduate degree in engineering from the University of Arizona. We've forgiven him for that. He went to work for Motorola, and he got very involved in the Motorola Six Sigma program, and ended up coming back here to do a master's and PhD, and he was my PhD student. I'm very happy to have him as a student. He worked for Motorola for a number of years, had some key management positions in production and in quality. He left Motorola and went to work in California for a company, Mindspeed, which did a lot of semiconductor work as well. He got interested in winemaking because he had a neighbor across the street, a guy named Chuck Belante, who was running a wine co-op. And I got involved with Chuck and met him. And a few years ago, a group of us sort of got together with Chuck, and we started a small boutique urban winery in Southern California. And we run some wine blending experiments every year, and they turn out to be mixture experiments. And so Dan is going to talk with you about some of our winemaking, some of our wine blending experiments. If you go back to some of the earlier fireside chats that we did in this program, I gave you an introduction to using fractional factorial designs for developing a winemaking process. This is kind of different. We've already got the wine made, and now we're blending it to get a superior product. So with that, I'm going to turn it over to Dan and let him tell you all about some of our wine blending experiments.
Well, hello everybody. Yeah, I appreciate the introduction, and I'm really happy to be here. This is a fun topic to chat about and so forth. So I'm going to continue with a few slides here. I'll share the screen just to kind of carry the story, and then I'll tell you a little bit about how we go through the process and so forth. And Professor Montgomery will chip in as well, and we can tell you a little bit of stories about our winemaker. He's kind of quite a fun person and so forth, but interesting fellow, and kind of take you through the stories as to when I got started in this process and where we are today, maybe a little bit. Okay, so I'm going to share my screen, and I will do that just like this. I'm going to ask, hey Doug, can you see my screen?
Yes.
Got it. Great.
I can see it.
Okay, so I'm just going to start with the story, right? How this all began, and basically a fellow named Chuck Belante. Well, he's been running the Belante Family Winery Co-op, and it's a garagista is what they would call it in France, since 2000. So for a lot of years now, 21 years now, and so forth. He runs it out of his garage. My wife and I joined Chuck's co-op in 2007 vintage when he and his family moved in across the street from us in Tustin, California. And so he bought this house because it had an interesting garage structure. It had a 4-car garage, which is unusual, but it had a normal 2-car garage, and then it had a tandem 2-car garage. And what he did is he took the back half of that 2-car garage, that tandem one, and insulated it, put a cooler on it, and turned it into a wine cellar that he could basically move barrels of wine in and out of. And then the front half of that garage, during winemaking times of the year and so forth, we would be manufacturing wine in the front half, right? The fermentation, things like that, pressing, bottling, and so forth. And so this was his garagista. He invited me to join the co-op and so forth, and my wife was traveling. My wife travels the world as a Lean Six Sigma consultant, and another one of Doug's graduate students. But she wasn't home, so I joined the co-op anyway, right, for both of us. And each year we were making back then about 100 cases of Syrah from basically 3 different vineyards, right? And later on, we added some other stuff like Viognier, a white wine, and we added Pinot Noir and so forth. And that bumped our capacity up to, or our production rate up to about 150 cases. Now that's a lot of wine when you think about it, right? But that's pretty small from a professional winemaking business. That's not very much at all. But anyway, we're making quite a bit of wine, and I was getting more than my fair share. So I started sharing some of this. We come back to Phoenix. Our families, or at least my families, were in Phoenix. Doug and Cheryl are in Phoenix. We'd come back and we'd certainly haul some of our wine there, and then and we'd have, when Doug and Cheryl would come visit, we would share the wine. So we drank a lot of this wine, and it's good wine. In fact, because we're hobbyists, we bought really good grapes. We had a access through a friend of a friend kind of a thing to buy really good grapes from the Santa Barbara area, and expensive grapes, right? And we bought them in small quantities, but we bought expensive grapes. And as a result, we could make some really good wine because we could pay very close attention to every detail about each of the barrels that we were making. So that's when, Doug, in fact, it was, Professor Montgomery here is the one who said, said to me, hey, what do you think? You think we can talk Chuck into going professional, right? We'll tell, let's tell him that we'll chip in, we'll help fund the endeavor and be partners and so forth. And boy, and after about 3 or 4 years of pestering Chuck, he finally decided to make the plunge. Said we only buy good quality grapes. We do. We buy the best that we can get our hands on. We have all the equipment. This wasn't stuff that you're doing in like bottles and jugs and you're doing in the bathtub or something like that. We had all the equipment, just small scale. I'll show you some pictures of that. But we had a press. We had a crusher destemmer machine. We had we used stainless steel tanks when we're doing fermentation. We would buy new oak barrels and stuff like that, just like the big people, right? And so forth. And like all winemakers, as I was kind of my just getting to know Chuck in the wine business and so forth, he would find different blends prior to bottling. So he would do his own little samples. He'd pull little samples. They have this, they call it a thief, and so it's this little gizmo that you can stick in the barrel, and you can pull out samples of wine from the barrel pretty easily. It's called a wine thief. And so he would make these throughout the year of making wine. He would be sampling the barrels, and he'd start to come up with ideas as to how he was going to blend them, right, and to produce the best overall wines that he could produce. This is where I saw the opportunity to help. So I said, hey, Chuck, why don't we run an experiment, a designed experiment? That's kind of like what I do for a living, and it's a lot of fun, and et cetera, et cetera. I was expecting a little more pushback from him, because when you get to know Chuck, you kind of realize that he not that he's not so against new ideas, but he thinks he's smarter than the rest of us. Right, Doug?
Yeah, he definitely has an ego problem.
A little bit. We pick on him a bit, but he's a chemical engineer, and he believes chemical engineers are at the top of the food chain, right? And so, and he will tell you that openly anytime in the tasting room and so forth if you ask him. So, and even if you don't ask him. But being an engineer and he understands modeling and a little bit of experimentation, like especially chemical engineers. Doug, I think you get a whole bunch of chemical engineers signed up for this DOE class.
Yeah. Chemical engineers take to this a whole idea of experimental design quite easily.
Yeah. And so he said, sure, let's do it. But rather than opening it up to the whole co-op, we were going to do this kind of secretively on a Thursday night, right? Because and then the following Saturday, he was inviting whatever co-op members chose to come, wanted to come on that Saturday, that we would decide the blends that we were going to choose. So we'd make some samples and tell people you can have this, and so forth, or this, and decide what they wanted. And then we would plan bottling a couple weeks later and blend it all and bottle it all and be done for the year. So anyway, I said, well, so I was really excited about it. So he and I, just by ourselves, set up this experiment. So give you a little rundown on the process, though. Like I said, for the co-op, you would buy into the co-op in February when Chuck ordered the grapes, because that's when he had to place an order, and he needed to make sure that we were all going to really be there to participate and to and pay for this when the time came to harvest and pay for them. So we would have to buy into it. I believe it was at the time $425 that was the co-op fee. That would get you 2 cases of wine when you're done. And if you wanted to buy 2 shares of the co-op, well, then you get 4 cases of wine and so forth. So that was in February. September, October, the grapes kind of are hauled from the vineyard to the winery in 1,000-pound bins. We had a fruit bin and so forth like that, so we could go pick it up. There's our little crusher to stemmer. It's puncturing the skins, and it's removing most of the stems and so forth. You can see we're just doing this right out there in the street. And then we throw them into some tanks. So you got stainless steel tanks and so forth. And we macerate for 5 days at 55 degrees. So we could roll these into the cellar, and it allows the juice and the skins. When you're making red wine, the color and the flavor, much of the flavor, the tannins, comes from the skins. And so if you just crush it and remove the skins, you'll have a white wine or something that's maybe a little bit of a yellow or a hint of red, but for the most part, it'll be kind of white wine. So by leaving the skins in the tank and so forth and get in contact, it removes that ruby red color. So anyway, that's what we're doing there. Yeast is added to the fermentation about 7 to 10 days. And we make a dry wine, so we let the yeast rip until it's done ripping, right? And all the sugars in the grape juice is consumed into alcohol. During this time, the cap must be punched down. I used to do this every once in a while, especially if Chuck couldn't get there. I'd go run across the street and I would punch, you'd try to do it a few times a day just to keep the skins in contact with as much of the juice. What happens is the fermentation and the gases take the skins and lift them to the surface. And so you kind of punch it down and so forth. The wine is then pressed and separated from the juice and the skins and the seeds. That's we got a small basket press. I mean, the big wineries have big presses. We have a small basket press. Then we put the juice back in the stainless steel tanks. After a week or so in the tanks, what happens is that there's a lot of crap. The wine after you go through this process is quite murky. I mean, it's not translucent, the nice ruby translucent. It kind of looks like you got milk added to it. So it's pretty murky. It's chunky. It's got seeds in it. It's got little skin bits in it. It's got bugs in it and so forth. We always kind of state that a really good year is when you get a few earwigs crawling in the wines, because if the earwigs like the grapes, that's kind of a true statement. So you kind of sort of get it off, but you don't get everything off. Anyway, but all the crap settles to the bottom of the tank. Not all of it, but much of it. And then we pump off the wine on the top and leave the crap behind and hose it out. And then we put it into barrels. Back in this picture, we were using 30-gallon barrels. We ended up moving up to 60-gallon barrels as well, and so forth in this process. But racking is done every couple of months because the stuff continues to settle, right? Now, a lot of high-volume winemakers will use filtering systems. They'll pump it through a filter, but the filter adds a little bit of flavor to the wine, as you might imagine. And so if you don't want to do that, you use we do the unfiltered, unfined kind of a process. So to remove the solids until eventually all the crap is pretty much has been settled out, and you just got nice red translucent wine. After about 11 months, the wine is, the winemakers determine the best blends via the designed experiment, and we bottle them. And we've got a little bottling machine there. It's got a blurry picture. I apologize for that, but it's a little bottling machine that does 5 bottles at a time. It's manual, but it fills them and so forth. Okay, and then we've got a corker, a manual corker and so forth, and that's what we did. That was our process. So here's the constraints. So when running this experiment, the problem is there are constraints in the winemaking business. And And the first one is the fact that it's a mixture experiment and all the constraints that Professor Montgomery just mentioned, right? So enough said about that. Another problem we had, I call it a constraint, but this might be a problem. We had one experienced winemaker, that was Chuck. And we had lots of experienced drinkers, and that's the rest of us in the co-op, right? So we're good at drinking. We rely on him to be the winemaker at the time. Limited amount of time to run the experiment. So because especially because we're a co-op, and even today to some extent as we're professionals, we really don't have that much time to run the experiment. So it wasn't like we could sit there and run a week's worth of series of experiments and stuff like that. Because these experiments would ultimately be run with the co-op members, we had a couple, 3-4 hours, maybe, to actually run the experiment and do the analysis and so forth. So we couldn't run really lengthy experiments over a long period of time. There's a limit, there's a constraint on how many experimental runs you can use. Now I'm going to get back to this. I determined that to be 25 max, no more than 25 runs. And basically what we would do is we'd make these blends up using the graduated cylinder, 25 milliliters of this, 12 milliliters of this, whatever, and we dump it into a glass, swirl it around to mix it, and then we made a series of glasses along the table or counter, and so we labeled them and so forth. I think I had some pictures of that too. But 25 max. I'll explain that in a little bit as to why that needed to be a constraint and not do more. If you want to call a wine a Syrah or a Cabernet or a Pinot Noir, then 75% of that particular varietal must be included in the wine. So if you go off and buy yourself a bottle of Cabernet, it's possible it's 100% Cabernet, but it's more than likely it has a blend of some other Bordeaux style wines mixed into it, right? And so forth. But at least 75% of it is a Cabernet. Okay, you might have a little Merlot in there, you might have a little Cab Franc and so forth. So same thing with our Syrahs that we were making, right? That's a Rhone style wine, and there's a whole bunch of other things that you can blend in there, and people do. Grenache, Mourvedre, a little Viognier, which is a white wine, are very common, right? But there's a handful of others as well that can be blended in. So what you have to do though is you have to keep 75% or more for the wine to be called a varietal. We weren't too worried about that as a co-op, but we're very concerned about that today. Now, 85% must be included to label the wine a specific appellation. So if I want to call it Napa Valley, right? Or if I want to call it Santa Barbara, or if I want to call it the Santa Rita Hills, or some of these appellations, well, that's a constraint as well. So if I'm getting grapes from different parts of we buying from the Santa Barbara area, but there's different appellations in there. If I want to call it an appellation, then 85%. And then the other one was sometimes you want to call things a specific vineyard because that makes it sound a little more snooty, and people pay more money for that. So if you want to call it this is a Watch Hill vineyard, and you'll see that on bottles, and you'll see that they tend to be priced a bit more. Well, then most of the grapes have to come from that vineyard, right? So these are obvious constraints, right? Obvious constraints, especially if I want to blend in a little Mourvedre, a little Grenache, a little Viognier into the wine. Well, I can't do too much of that, or I'll break one of these rules. And in our case, we must use all the grapes. Some of the really big producers, they can actually throw away a little bit, or literally what they do is they will sell it off to a jug wine maker, and they will blend it into some sort of big hopper and make jug wine out of it. The big producers, the Beringers, the Mondavis, and so forth. They make different grades of wine, but if they got some leftover stuff that they don't know what to do with it, there are people out there that will buy it from them and make a jug wine.
Dan, so, this is probably where your $2 chuck at Trader Joe's comes from.
Yes, yes, and so forth, right?
Right.
And yes, and so, but in our case, because every co-op member chipped in money, $425 in February, for at least for each share that they bought. we only buy that many grapes, right? And so we kind of have to, we can't throw anything away. We can't say, well, you know, we have to provide the 2 cases per share at the end of bottling. So that's a constraint, right? So wine drinkers are inexperienced winemakers, right? Most do not know how to score wine. So we've got all these, we've got a handful of people of our co-op members that show up for this event, for the experiments, do not know how to score the wines, right? And I'd say a lot of experienced wine drinkers and so forth, and so a lot of people don't know, you know, you read the labels, you go to Costco, you go to Total Wine, you go to Bevmo, and you'll see, ooh, they got these cards that says, ooh, this one scored 89, and you say, ooh, that sounds pretty good, and ooh, 90, that's even better. Well, it turns out the scoring system that's used for scoring wines is actually, it's not 0 to 100, it's actually 50 to 100. The worst wine ever is a score of 50, right? So it goes between 50 and 100. And there's criteria for doing this and so forth. I'm telling you guys, it's kind of complex, takes a lot of experience. You got to go to one of those, you know, the schools and so forth. You got to drink. There's a whole process for learning how to do this properly. The members of the co-op don't know how to do this properly, right? So I can't sit there and say, okay, no, everybody score the wine and so forth, and let's use that. Not going to happen. Those who do know how to score wines require a lot more time than what we have available. So even if people knew how to score the wines, it's actually, there's a points, you got to add up all these little points for the nose, the taste, the finish, the acidity, the bite of the tip of the tongue, the back of the tongue. You've got the, you know, all this stuff. You got how long do you think it's going to age, all that kind of stuff, right? So there's ageability, all these kinds of criteria. Yeah, it's actually a little bit complex. The wines in the glass change over time. So if you set up an experiment, especially a young wine, these are out of the barrel, these are barrel samples, right? If you leave them in the glass for you know, a couple hours, it's a different tasting and smelling wine than when you first put it in the glass, right? It evolves in the glass over, and you guys have probably experienced that as well. You open up a bottle of wine, and you know, an hour later you say, ooh, this seems better, right? And maybe it's because you drank half the bottle already and it just seems better because of that. But more than likely it probably did open, they call it open up, right? And so forth. It probably did improve. So we have those constraints as well. So I employed a forced rank process for our nose, taste, and overall response variables. So we had these are our response variables. We had 3, so we're going to fit 3 models. 1 for nose, 1 for taste, and 1 for overall. And the overall is kind of more like the finish and so forth on the wine. Our OR faculty, so when I started at ASU, I'd been doing this wine making for the process, and I started sharing with some of them, and they criticized me for using this method, right? Oh, you got a better method. These are faculty folks, right? These are academics, I'd call them, but they criticized me for using this method. There may be other methods, but it turns out, especially with inexperienced people, this works really, really well, the forced rank. Many years ago, Professor Montgomery showed us in a class the forced rank scoring method from one of the examples he was kind of giving us in the lecture and so forth. And I had used that many times in semiconductors. So, you know, I'm running an experiment with a bunch of wafers and stuff like that, varying temperatures, pressures, whatevers, and you know, and you're measuring thicknesses and geometries as your primary measures. But I always finished with a qualitative visual measure, and I just had my engineers rank them, right? Tell me we got a 16-run experiment, rank them from 1 to 16 based on just qualitatively looking at it. Because there are certain things in looking at semiconductor wafers that you say, ooh, that one's probably not very good. It looks a little cloudy, that kind of thing, right? So I use it for blending. We use it for blending. Our first mixture experiment was the 2007 vintage. Jack McGinley Watchhill in 2 different barrels of low trace barrels. So we had 4 different Syrah barrels 4 different Syrahs were blending. This was a simple 4-component simplex design, one of those that actually Professor Montgomery showed you in the slides. Looked like that. So it's that pyramid thing, right? And the dots represent the different runs on the experiment. we ended up, you know, when we fit the models, we fit models for, I said, nose, taste, and then overall parameter. We use something called a desirability function to kind of, it's kind of like a weighting scheme. It's a way of combining these multiple responses into one overall desirability, right? The, you know, overall kind of numerical quality measure. And that's what these contour plots represent, right? Finding the optimal overall desirability. And in the contour, blue is the best, it's the peak, right? And so forth. Blue, then green, then yellow, then orange as it's progressively getting worse, right? So clearly our optimal solution is right there in 2007 vintage. Right there. It's about 40% Lowe's Trace barrels, barrel 1, and 60% Lowe's Trace barrel 2. Optimal solution. But now, you know, we still had a bunch of other stuff left over. What the heck do we do with that? So then what we did is we said, okay, you know, and what was left over combined, you know, just throw it all together into, I always call it residuals, right? It's what's left over. The residuals weren't very good. And so I said, well, whoa, Chuck, let's do this. Let's run another, you know, with what's left over. Let's look at everything that's left over, and using the model, figure out, well, where's the next best thing to do, right? So we came up with a robust solution with what was left over, and that was about 35% Jack McGinley and 65% Watch Hill, right? Ooh, now there's still a little bit of wine left over. There's a little bit of Jack McGinley left over. There's a little bit of Lowe's Trace barrels. Lowe's Trace barrels number 1 barrel was left over, and that ended up being that in the plot ends up being someplace around there, right? And that's not bad either. Green is not bad. Blue is best. Green is not bad. So we did pretty good, right? So how did we get here? I'm going to go through this kind of quickly because I don't want to run through time. But we used the models that we created from those design experiments. It's pretty easy to find the optimal solution is, especially with software like Jump and Minitab and so forth. One unfortunate possible outcome is that a very small yield of optimal quality wine, which means you got a whole boatload of kind of maybe not so optimal, even crappy wine, right? It's also possible, as I said, it could be really bad wine kind of all mixed together. So we use the models of the response variables and desirability function to adjust the optimal. Maybe I can tweak things a little bit such that I get more of this, call it optimal solution, without affecting the quality overall desirability too much. You know, I can add a little more of this, I can tweak it to get more of that and improve the residuals at the same time. So that's what we were doing, guys. So we started doing largely, we'd come up with an optimal solution, and very often we'd have some sort of intermediary robust solution, and then we'd have these final residuals, which may or may not be any good, but we wouldn't have that much of it for our shareholders. In 2008, we used the simplex centroid design again with 15 runs, same experiment. But in 2009, ooh, we got to play with Grenache. And in 2010, we had Grenache and Mourvèdre, right? Now that gets pretty exciting. But now I'm back to that constraint and Professor Montgomery is talking about, I'm not going to have this nice, beautiful little triangular simplex kind of a thing, right? I'm going to have some sort of polyhedron that's got these, and so I'm going to have to do a little different kind of an experiment. Remember the varietal constraint, I mentioned that. So we ran it like this. You could do 100% of the different Syrahs, but 30% max on the Grenache, 15% max on the Mourvèdre. Those are a little overkill, but I always kind of push things beyond the practical experimental range, or the practical where we would ultimately blend range. I think it fits a better model. We did the optimal 36 runs, right? Sounds pretty cool, doesn't it? 36 runs. I've got 3 Syrahs, I've got a Grenache, I've got a Mourvèdre. 36 runs, right? I got 5 barrels. Remember that? I said, don't go over 25. Well, this is why that came into play. Us inexperienced winemakers, we don't sip and spit. We sip and drink. And then we sip and drink again. And then we sip. And when you got 36 runs, about halfway through the experiment, everything started tasting great. I mean, our winemakers were all saying, oh, good grief, this is the best ever. Just bottle it. Bottle this one like it is. I'll be happy, right? We're saying, oh, you know, so we lost a bit of the objective data for the experiment because we had drunk too much, right? Everything was just fantastic. Back to 2011, I was back to 15 runs, okay? That year we had 9 winemakers tasting, so it was another challenge. This is something that our friend Doug and I have a friend named Brad Jones over at SAS, and he's kind of an architect of Jump, and he created this thing called a profiler that we're using. So you can see I've got nose, taste, overall, and I got the desirability function. So we use this to kind of tweak around to determine our solutions. And now looking at the bottom here, I've got Jack McGinley, Thompson, Martian was a vineyard. I've got a mixed barrel, and then my desirability for the 2011. Then what I do is I create an Excel spreadsheet that says I've got 30 gallons of Jack, I got 60 gallons of Thompson, I got 90 gallons of Martian, I got 30 gallons of this mixed barrel. Basically, what do you do with all the partials after you're crushing this stuff? And we had a total of 210 gallons of wine. If I were to just throw it all together into everything, you know, what do I get in the way of the quality? This is my score on nose, taste, overall, and then my desirability function after running the experiment. So I'm playing with the models. The optimal solution this year, if I could do it, was 100% Jack. Jack was the best. Just use 100% Jack and you're good to go. The problem is I only got 30 gallons of Jack, so everybody's only going to get a couple of bottles, right? That's not any good. And then the residuals, notice that the desirability on the Jack was really good. You know, higher is better, up to 1. The residuals was awful, right? So we came up with a few different ways of splitting this up. The one that we ended up using, I call it Syrah 6 because we came up with a half a dozen different schemes on this thing, was the optimal solution was 71% Jack and 29% Thompson. That gave us a score. It only dropped our desirability by 2 points, but it gave us a lot more wine. It gave us 17 cases, it gave us a lot more wine to share. So everybody was going to get 6, every shareholder, each share would get 6 bottles of this, whereas this other one, each shareholder only got 4, right? So, and then the suboptimal solution, kind of that intermediate wine, had a desirability that wasn't bad, 0.68, and everybody's going to get 12 of those. So that was really good. And then of the residuals, which wasn't very good at all, but people only ended up with about 6 bottles of that. So this was our optimal solution, okay? And graphically, it looked like this. There's the plots, the ternary plots of that. Martian was just a kind of a bad vineyard for us. That was the only time we ever used them, and did it again. Today, finishing up the story, today, beginning with 2015, we became professionals. We ran our first mixture experiments as professionals at the winemaking facility on June 3rd and 4th, 2016. Our grand opening was 2017. We've only made 500 cases that year. We're now producing about 1,200 cases. There's our experiment. You can see Doug, Mike's a shareholder. That's Chuck Palante, our winemaker. You can see us setting up the glasses. We label them all. He's got his graduated cylinder, and we're going to do our blending. There he goes, right? Something as simple as that. You can see all the barrels behind us. We're happy. We've been running blending experiments all day, so we were quite pleased with ourselves at that point. It's cold in there. It's 55 degrees in there, so we're dressed kind of a little bit warm, except Chuck, because he's Chuck. There's some pictures. There's the experiment, right? You can see what we're doing. You can see I'm climbing up to grab some wine out of one of our barrels using the thief. There's our tasting room. That's my lovely wife taking another picture. There's Chuckles there at the tasting room. We're doing a release party and so forth. Today, as professionals, the experiments only get bigger. Consider blocking, maybe do that 25 glass constraint. Other constraints, the appellations and so forth are much more serious now than they were as a co-op. Our time for running the experiment is still constrained because but should we still use a forced rank? Mickey Manzanito, one of our friends, also one of Professor Montgomery's doctoral students, she actually did some work on categorical responses in mixture experiments. Right? Seems like maybe something we should probably consider. Anyway, maybe some other algorithms to identify optimal solutions. And path. So accolades from experts. We're drinking the wine. That's Scott. That's Stu Hunter. Scott Kowalski. He's an architect, one of the chief architects for Minitab. Obviously, Professor Montgomery and Cheryl, Dr. Jennings, and so forth. I'm gonna just pause for a second, just because people generally ask us. I'm gonna stop sharing. This is one of our old bottles of wine, right? I always put the ternary plot on it. This was the optimal solution from 2008. And Doug and I we're gonna get together at the Fireside chat and open up a bottle of wine and drink it in front of you guys, but we were told that was a bad idea. And then because of COVID constraints, I can't be there.
And it's kind of early in the day for me to be drinking wine, so you know.
Yeah, but if you don't start in the mornings, right?
Yeah,
drink all day.
You can't. My favorite, one of my favorite sayings is you can't drink all day if you don't start in the morning. So.
Yep.
Okay,
guys, I appreciate the time. I know I took probably an extra 5 minutes. I hope we got time for some questions.
Yeah,
but it's a lot of fun.
I really appreciate you doing this. These blending experiments really are super important in terms of improving the quality of the product. And a lot of people in the wine business do these very informally. And I think one of the things that we do that makes our wine exceptionally good is that we have a very rigorous, scientifically based approach to doing this. Okay, we have a few minutes, maybe about 10 minutes left for some questions. And we've got some that have come in, and let me take a shot at running through these. This question comes out of the course on experimental design basics. Why is the assumption of homogeneity of variance required everywhere, like in the ANOVA regression and the t-test? Well, the assumption of equal variances is required in the theoretical development of the test statistic. So when you develop the F statistic for the ANOVA or the T statistic for say the two-sample hypothesis testing problem or fitting linear regression models, you have to make that assumption in order for the mathematics to work out correctly. But it turns out that the T and the F tests that we use in linear models and in hypothesis testing, those tests are pretty insensitive to that equal variance assumption. But you do need to check the equal variance assumption, and residual plotting is the way we do that. Minor, small, moderate departures in that assumption are not going to be crucial, but big departures will be. They will affect the sensitivity and the power of the test. So it's a theoretically required assumption, but it turns out that the procedures are fairly robust to that. Okay, next question. What are the assumptions required by the Plackett-Berman design? In the Plackett-Berman design, every main effect is aliased with a linear combination of two-factor interactions. In fact, it's partially aliased. Every main effect is partially aliased with every two-factor interaction involving that main effect. So typically you would use these designs in situations where you have a fairly large number of variables and where you don't want to invest a lot of resources in the original experiment. And so you're willing to make some errors. You're willing to maybe think that some main effects are important when they really aren't, because they're really, what you're really seeing is a two-factor interaction term that's aliased with that main effect. I think Plackett-Berman designs have a lot of uses, and they are versions of what we call non-regular designs. And if you have the right analysis tools to deal with the data from these experiments, they can be very powerful. One of our early guests on the Fireside Chats was Carly Metcalf, who by the way did the jump lectures for our MOOC, and she talked about her research, which has been developing methods for analyzing non-regular designs, and she has developed a class of methods called AIMS, Alias Informed Model Selection, which is a really great method for using with these non-regular designs. Now, we haven't tried this with placket Burma designs, but I suspect variations of that method would be okay, would work well. Traditionally, people use things like a stepwise regression, and that can work pretty well. Okay, question from the response surfaces course. What does a Pareto chart describe? Well, the Pareto chart is simply a way of taking, typically we use it with defect data. And what you do is you plot, say, defects by type. Okay, so type 1, type 2, type 3, type 4, type 5. And the Pareto chart is just a graphical description of the frequency with which various types of defects occur. In general, it's a description of the frequency with which various events occur. Dr. Joe Duran used to say that the Pareto chart helps separate the vital few from the trivial many. Second question was, when we put factors into the central composite design, the experiments divided into blocks, what's the meaning of blocking? Well, in a central composite design, what we're doing when we block the design is we're running certain groups of a certain group of runs under one set of conditions, and then a second set of runs, let's say, under a different set of conditions, maybe different batches of raw material at different time periods. And in blocking in the CCD, usually one block is made up of the factorial portion. So you do all of those runs, let's say, from one batch of material. And then the axial runs form the next block. And so that set group of runs would be run under, say, a different set of conditions, a different set of material, okay? And then the center runs in the CCD are divided between the two blocks. And what this does is this allows you to eliminate this nuisance variable, like the two different batches of material. Basically, blocking is a technique for running an experiment where you have a nuisance factor, like different batches of material or different time periods or different operators, and you want to eliminate the variability that nuisance factor produces. That's what blocking does. I've used a mixture design, 3 components, but the region gets really small. Yes, it probably is a really good idea, because the reason the region is small is that the factors have fairly large effects over that region. So I think this is an ideal situation for using mixtures. Thanks for sharing your experience with winemaking. One question: did you have issues with the residual analysis because your response variable is not continuous? When we did this in our winemaking experiments, like I talked about in a previous Fireside Chat, not so much so, because what you're doing is you're analyzing the average rank across all of your panel. And so that average rank becomes more like a continuous factor. And so I don't think I ever had any problems. Dan, you didn't see any problems with the experiments either, I don't think.
When we're using multiple, especially, you got 4 or 5 or more people, and what we were doing is we were summing up their scores, and as you know, if you sum random numbers, it kind of sort of makes it.
If you average enough of those numbers, they're gonna sort of be normal-like anyway. So no, I think if you use average rank across several testers, you really don't have much of a problem.
I once, but when we had just a couple or something like that, which isn't often, but there's sometimes a transformation helped us with that
Yeah.
a little bit, you know, a logit transformation or something like that, which would kind of make sense. Sometimes that kind of that helped us with our residual analysis did violate under the assumptions, and we would generally could still correct it with a transformation.
So here's a question that says, thanks a lot. Are there some papers that I can review about this study? And the short answer to that is I have been trying to beat Dan McCarville over the head for several years to write up these blending experiments and get them in print, because they're really beautiful examples of mixture experiments. And he keeps promising me to do it, and maybe one of these days he'll actually do it. Okay, but sadly the answer to that's no.
Sorry about that.
Okay, what is meant by detecting effects of size 2 sigma? Well, what that means is that when you change that factor from the low level up to the high level, the average change in the response variable is twice the standard deviation of the random noise in the system. So that's what we mean by 2 sigma effect. And can you calculate a sample size or amount of replication for a given significance level using an equation? Yes, you can for some cases. For example, for the 1 sample and 2 sample t-tests and z-tests, there are sample size equations, and they can be found in most basic statistics books. But when you get into the more complicated types of experiments, there aren't really simple sample size formulas. Okay, we're running up against our 1 hour time frame. I'm getting the signal from from Dustin and Megan, and so once again, with thanks to Dan McCarville, we're going to sign off. And I think we have a few other questions that we'll deal with, and we'll try to get the answers out on Coursera. Thanks a lot.